Welcome back to this lesson, friends. In this one, limits of inverse trig functions using graphs. So I'm deliberately using graphs because they help us understand things better, but look at this function here. So this says f of x is equal here to the tangent inverse of x. Because we're doing calculus, I kind of assume that you know how to generate this. But as a brief reminder, you can take the basic tangent graph, one branch of it around 0, and then mirror it across y equals x, and then it becomes the inverse tangent. Having said that, let's see what limits we can take here. So one limit might be to see what happens, for example, at infinity. Say, as x approaches negative infinity this way. Then we can see that the values of the function are kind of heading this way, which means that the corresponding y coordinates are going down towards negative pi over 2, but from above. In other words, I would say the limit, as x approaches here negative infinity, of the following, f of x, where f of x is our tangent inverse, this would be equal then to the following. Negative pi over 2. That's one limit that we can take. What happens around 0? Let's study that limit a little bit. So when x approaches 0 from the left side, the values of the function move up this way. In other words, they're approaching 0 from below. When x approaches 0 from the right side, the values of the function basically would then approach 0 from above this way. So the point is the following then in terms of a limit that we can write down. The limit as x approaches 0, I don't need a plus or minus because it's the same limit for both sides of f of x in this case would be just equal to 0. Another common limit that we do here is this one. Take a look, for example. What happens? I'm going to do this one, let's see, in gray. When x approaches 1, look very carefully, from the left side. Well, the values of the function in that case approach pi over 4 from below. When x approaches 1 from the right side, the values of the function approach pi over 4 from above. If you have trouble seeing that properly, take a look. At 1 itself, when that goes in, carefully follow the arrows, you see pi over 4 comes out. That's why the limit is as such. So you can write down the following limit then. The limit as x approaches 1, from left and right is the same limit of the following. F of x is then equal here to pi over 4. One other common limit here is this one. What happens, for example, when x goes towards positive infinity? And you see that basically the points on the graph move this way, but that also means, remember, that the corresponding y coordinates of those points move up towards pi over 2, but from below pi over 2. So in other words, as a limit statement, I might say the following here. The limit, as x approaches positive infinity, of f of x is then equal here to, this is a value that we never reach, it's just a value that we approach. It's a horizontal asymptote. And also remember that what are the two vertical asymptotes for the basic tangent function? One at negative pi over 2 and one at positive pi over 2. Those become horizontal asymptotes when you mirror that one branch across y equals x to generate the inverse tangent function. That's why the graph looks like this. Let's move on. Here are some additional ones. So this one is the following. I'm going to call this one, say, h of x. And this is the cosine inverse function this way. Let's find some limits in here. Well, I can tell, for example, that when x approaches 1 from the left side, right, that basically the points on the graph move down this way, which means that the corresponding y coordinates move towards 0. So I would say the following. The limit as x approaches 1 from the left of h of x in this case, this is equal to 0. Another limit that we can do here, let's see here. I'm going to do this one in green. So when x approaches 0 from the right side, the points along the graph move this way. When x approaches 0 from the left side, the points along the graph move this way, which means that the corresponding y coordinates move towards pi over 2, from below and above pi over 2. So for that reason, I can make the following claim. The limit as x approaches 0 of h of x is then equal here to pi over 2. One last limit that we can take here. We can approach negative 1 from the right side. The points along the graph move this way, which means that the corresponding y coordinates move up from below towards pi, which means I can write down the following limit. The limit as x approaches negative 1 from the right side of h of x, that's equal here to pi. This last graph is the sine inverse function graph, so I'm going to write the following here. Say p of x is equal to sine inverse of x. On the left side, when x approaches negative 1 from the right side, the points move down this way, which means that the corresponding y coordinates are moving down towards negative pi over 2. So I can say the limit as x approaches here negative 1 from the right side of p of x is just equal to negative pi over 2. Let's also see what happens around 0, so I'm going to use green for that. When x approaches 0 from the left side, points along the graph move this way, which means that the y coordinates are moving towards 0 from below. When x approaches 0 from the right side, points along the graph are going this way, which means the corresponding y coordinates are moving towards 0 from above. So I can say the following then, in terms of a limit that we can write down, that the limit as x approaches 0 of p of x here, that's equal to 0. Let's do one last limit here. Let me do that one in this color, black. When x approaches 1 from the left side, then the points along the graph move this way, which means that the corresponding y coordinates move up towards pi over 2. Which means, therefore, that the limit looks like the following. The limit here as x approaches, say, 1 from the left side, so put a negative up there, of p of x, that's equal then to pi over 2. Thank you so much for watching. Please leave a like, please subscribe. I will see you in another video.